How do quarks stick together? Protons and neutrons are held intact by the strong force, which bonds quarks via subatomic particles called gluons. But these gluons don't actually physically attach quarks to each other. The truth is more complicated. Instead, quarks are glued together through a mysterious property called color charge, which ironically has little to do with charge or color. Instead, whereas gravity acts in one direction and magnetism acts in two, color charge acts in three. Inside every proton and neutron, these three charges are represented through three quarks of three different types: red, green, and blue. Each of these colors also has a corresponding anti-color. But to fully understand how color charge works, we first must understand why it exists. You see, without color charge, matter as we know it would tear itself apart. This is because without color charge, quarks all have the same quantum properties, same spin, same energy, same everything. And if every quark in the universe was exactly the same, they couldn't fit together into the small space that makes up a proton or a neutron. Physical laws like the Pauli exclusion principle literally prevent this from happening. So the only way quarks could share this very small space is if a secret property differentiated them from each other, which is exactly what color charge does. Colors in every proton and neutron must be unique and must add up such that the particle appears to be color neutral. This is achievable only when equal amounts of all colors combine, or when colors and anticolors cancel each other out. And so because of this, you can think of each quark as a color that combines into white pinpricks of light, which make up all the matter we see. But how does color charge actually bind quarks to each other? Let's explain using a simpler analogy, a game of catch. You can think of each proton or neutron as a self-contained game between three quarks. Each quark is assigned a distinct color. As mentioned before, all colors must cancel out, but there's no limit to the amount of players in a game. You could have 2 or 3 or 5 or even more. This actually means the amount of quarks in a particle doesn't always have to be 3. This is just the most stable combination that exists. For example, objects called pentaquarks are made up of 5 quarks. In each game, each quark holds onto a gluon to start, and they pass them to their neighbor as fast as they can. Gluons are always made up of a color and an anti-color. When a gluon is received by a quark, its colors are absorbed and combined into the quark's own color. For instance, a red quark intercepts a gluon that is both blue and anti-red. The red and anti-red cancel each other out, so only the blue color remains. So the quark becomes blue, and when it ejects the gluon, it becomes red again. In every interaction, color is conserved. As the game of catch progresses, the color of quarks changes, but the balance of colors in the game always cancels out. The exchange of gluons between quarks creates a powerful field that ties them together. All quarks come in pairs or triplets for this exact reason, because due to this property, quarks can never be alone. If any two quarks drift too far apart, the energy in their bond increases. Two possibilities then arise. Either the quarks get closer together and return to a stable state, or the bond gets so powerful it frees both quarks and simply creates 2 more out of thin air. This is directly tied to the equation E = mc², which defines matter as a product of energy, and vice versa.